an announcement for those of you who cannot make the exam on the 10th. As I said, I would be happy to do another exam, but it turns out you also need the permission of the university. So if you want to take the exam on any other time, just send me an email and I'll give you the forms that you need to fill for that. Okay. So today we're going to talk about a new topic and actually basically a new parameter, which we will use a lot for parameterizations when you're using graphs. And that parameter is the Treewidth. Now, I can't pronounce this name correctly because this sound doesn't exist in my language. So whatever I say that is similar to this is what I'm saying. It's Treewidth. Okay. So here's where I want to start. Let's say we have a problem that is NP-hard, but it's easy on graphs that are just trees or forests. So for example, let's say I want to think about the problem of maximum independent sets. So in this problem, I just give you a graph and you have to tell me what is the maximum number of vertices that you can pick from this graph so that no two of these vertices have an edge between them. So what is the largest independent set in this graph? And this is, of course, an NP-hard problem. I'm not going to prove that. You can just search independent set NP-hardness and you will find all sorts of proofs for why this is NP-hard. But the thing I want to focus on is that the problem is easy if your graph is a tree. So if I just give you a tree, let's say something like this, and I ask you what is the largest independent set here. You can actually solve this problem with a simple dynamic programming. Okay, so let's say that at every vertex, okay, so let's say first I choose one of my vertices as the root. So this is the root, and now I can talk about children and parents and everything like that. So at every vertex V, I define two dynamic programming variables. I define dp of V0 and dp of V1. Now, dp of V0 is going to be the size of the largest independent set in the subtree of V that does not include V itself. Okay? Size of the largest independent set I, but I'm only considering the subtree of V. So if this is V, I'm only considering this part of my graph. In the subtree of V. And I'm also saying that I don't want my independent set to contain V itself. So such that V is not in I. Okay? And the second dynamic programming variable I'm going to define is exactly the same, except that V itself is going to be in I. So everything the same as above, except that at the end of it, I say V has to be in I. Now, of course, the largest independent set of the whole subtree is just going to be the maximum of these two cases, right? Because every independent set either contains V or it doesn't contain V. So if I can just compute these values, I can find the size of my largest independent set, and that would just be the maximum of dp of root 0 and dp of root 1. Okay, now how can I compute this? Well, that's also pretty easy. So let's say I want to compute dp of V0. What do I know here? I know that I want an independent set from this subtree, which might be much larger than this. And I know that V itself is not in there, right? So if I just remove V, this subtree down here, it will break down into several trees. So if I remove V, now I have several different trees. And these are disconnected. So in each one of them, I can just find the maximum independent set, right? So in other words, if the children of V are, let's say, U1 to UK, then I can say that dp of V0 is just the sum for j from 1 to k, dp of uj0 or dp of uj1, and we have to take the maximum. And oops, I don't have enough space. Sorry about that. So the sum of this maximum. Okay. Now, how about dp of v1? So in that case, I know that v itself is going to be in my independent set. So if v is in the independent set, then none of its children can be in the independent set. So dp of v1 is just going to be the same sum, but instead of taking the maximum, I know that none of these should be there, so it's just sum of dp of uj0. And of course, I have v itself in my independent set, so I have +1 at the end. Okay. So how much time does it take for me to compute all these dp variables? It's actually quite easy to show that this is linear time, right? Because whenever I'm at a vertex v, I'm computing this sum, and the time it takes for me to compute any of these sums is proportional to the number of children of v. So my total time is just linear. Okay. Now in this session, we want to just analyze this algorithm and see what are the main points that we are using in our reasoning. And can we somehow extend these main points to graphs that are not trees, but kind of look like trees? Okay. So first of all, the most important thing in my reasoning was that when I took this vertex v, and when I decided whether I want to have v in my independent set or not, then as soon as that was decided, whatever I did in each of the children was completely independent of any other child. Right? So here I said that if v is not in my independent set, then all of these are disconnected, and so I handle each one separately. And even if v is in my independent set, then I know that none of its children are in my independent set. And again, I handle each one of these subtrees separately. So what was the property of v that allowed me to do this? It's the fact that if I take v and remove it, the graph breaks down into a lot of different connected components. And especially, I'm just looking at the subtree of v, so I know exactly what the connected components are. They're just the subtrees of each of its children. So now suppose that I give you a graph, and I tell you that you can always find not just one vertex that breaks it into a bunch of different connected components, but always at most k vertices. So this is what I want you to imagine. I want you to imagine that I give you a graph G, and initially in the graph G, you can find a very small number of vertices so that they disconnect the graph, so that they're a cut. Okay? So in the graph G, I have maybe, let's say, k vertices here. And if I remove these k vertices, then G breaks down into a bunch of connected components. Okay? And then I want you to imagine that I can continue this in each one of these connected components. So let's say that, again, in this connected component, I can find a small number of vertices, maybe k vertices, so that they break disconnected components into two parts. And then I can do this for all of them, and I can do this recursively again and again. Okay? So if I have something like this, if I have a graph that can be, let's say, decomposed like this, right? Then I can extend my algorithm for finding a maximum independent set. And this graph here, it doesn't have to be a tree anymore, but it kind of looks like a tree, right? And I'm going to make that much more formal very soon. But let's just see what happens here. So here, when I had a tree, I could just take one vertex V, and that vertex was a cut. So I could just decide what I'm going to do in my cut, whether I'm going to put it in my independent set or not. And that would tell me immediately after I chose that everything else becomes independent of each other. So here I can probably do the same thing. So if I take my k vertices and I take all the 2 to the power of k different possibilities for which of these vertices are going to be in my independent set and which ones are not going to be in my independent set. Then as soon as I know that, whatever I do in any of these connected components is going to be completely independent of what I do in other connected components. And if I can then continue this process, if in any of these connected components I can again find a small cut of size k, then basically I have an algorithm that has a runtime of O(n) times 2 to the power of k. Because the algorithm is just like the algorithm on the tree, except that every time that I'm doing a dynamic programming, instead of considering 2 cases, I have to consider 2 to the power of k cases, because I have k vertices here. Okay? So this is the intuition behind the concept of Treewidth that I want to formally define right now. Basically, we want to find graphs that kind of look like trees in the sense that you can always find cuts of a small size. In a tree, you can always find a cut of size 1 because every vertex is a cut of size 1. But I want to have a definition that captures this intuition, that I can always find a small cut and break down my graph into 2 parts, or maybe even more than 2 parts. Okay. So let me erase this and then I'll give you the definition. Now, this definition might sound a little bit weird at the beginning, but you will get used to it. So let's say I have a graph. For example, let's say this is my graph. I have a triangle, and then I have one edge going out of each side. Okay. And let me give some numbers to my vertices. So let's say this is 1, 2, 3, 4, 5, 6. Now, the first idea is that I want to take this graph, which is not a tree because it has a cycle here, and I want to embed it into a tree. Okay? So let's say that I have a tree, and I'm going to create my tree like this. Now, this is just a tree. I can have any kind of tree. But now I want to somehow embed this graph into this tree. What do I mean by embedding? I mean that I want to take each one of my vertices in the original graph, and I want to assign a connected subtree on this side to that vertex. So, for example, I take vertex 1, and I say I want to put 1 here and here. Okay, the only rule is that whatever I choose here should be connected. So I can't put 1 here and here without putting it also here at the root. Okay, so I take my vertex 1 and I put it here and here. Let's say I take my vertex 2 and I put it here and here. I take my vertex 3, put it here and here. I take vertex 5 and maybe just put it here. I take vertex 6 and only put it here. I take vertex 4 and only put it here. Okay. So what are the rules that I have to have in this embedding? Well, the first rule is that each vertex of my original graph should be embedded in a connected subtree of my tree. Okay? That's the first rule. The second rule is that if 2 vertices in my original graph have an edge to each other, then they should meet here in the tree. Okay? So if, for example, I have vertex 1 and vertex 2, and there's an edge between 1 and 2, there should be some point in the tree where the embedding of 1, the embedding of 1 was this part, meets the embedding of 2, which is this part. And they meet here. Okay? So, why am I doing this? How does this help me at all? Like, let's say I want to again do independent set here. You see, now I can do independent sets, my independent set algorithm on trees, on this tree, and pretend like I'm actually doing it on the original graph. Right? These are going to give me the small cuts that I was looking for. So for example, here, if I take the vertices 1, 2, 3, and if I just decide what subset of these vertices is going to be in my independent set, then I know what happens to these 3 vertices. But if I remove these 3 vertices, then my graph is 3 connected components that are now disconnected from each other, and I can solve the independent set problem separately in each one of them. So you see, the whole idea of embedding this graph into a tree is so that we can apply our tree-based algorithms to the original graph. Okay, but now I'm going to give a more formal definition, which is basically equivalent to this embedding idea that I told you. And that's the definition of a tree decomposition. So this is called a tree decomposition of that graph. Okay, so this is my graph G, let's say with vertex set V and edge set E. And this is my tree decomposition T. And okay, let's say its vertex set is vertices of T and its edge set is just edges of T. Okay, actually, I would rather call its vertex set B, and you will see why so. Okay, so what is a tree decomposition? Okay, a tree decomposition of a graph G is just a tree which is like that. So I call its vertex set B. So it's a tree T, E, E, T, such that, now here's what I want to do. In my embedding definition, I said that I take every vertex of my original graph and I assign it to some connected subtree here. But I can look at it from the other side, and I can say each vertex of the tree contains a subset of vertices of the original graph. Okay? And that's what I'm going to do. So I'm going to say each vertex of the tree, each B in B, has a corresponding set of vertices. Has, let's call it V of B, which is a subset of the vertices of the original graph. Okay? Now, each one of these vertices of the tree are called a bag. Now, we call them a bag because they're basically containing a bag of vertices from the original graph. And that's why I used B here. And we also use the word bag because when we say vertex, we want to be sure which vertex we're talking about. So whenever I say vertex, I mean a vertex of the original graph. Whenever I say bag, I mean a vertex of the tree decomposition. Okay. So the first condition is that every bag has a bunch of vertices. But I, of course, want every vertex to appear somewhere in the tree decomposition. So my second condition is that every vertex of the original graph should appear in at least one bag. Or another way of writing this is that if you take the union over all bags of the set of vertices that appear in that bag, this union would just be the set of your vertices. So every vertex appears in at least one bag. Now, what else? Well, we said that if two vertices have an edge between them, then there should be a bag that contains both of them. So every vertex, sorry, every edge should also appear in some bag. Or in other words, for every edge, which is, let's say, from U to V, and it's in the edge set of my original graph, there should be some bag B such that it contains both endpoints of the edge. So such that both U and V are in V of B. Okay, and finally, when I was doing the embedding, I said that every vertex is going to be embedded in a connected subtree of my tree decomposition, right? So I have to say that as well. I have to say that every vertex appears in a connected subtree. But how can I say that? Well, this is, I want to say it from the point of view of this tree decomposition. So I can say something like this. Let's say I have two different bags in my tree decomposition. Let's say bag 1 and bag 2. And let's say that both of these bags contain a particular vertex. So for example, vertex V is both in bag 1 and bag 2. So what do I want to say? I want to say that V appears in a connected subtree. So if I take the bags that are on the path from B1 to B2 in the tree, so just consider the path that I have to take to go from one to the other. So V has to appear in all of these bags as well, because that's the only way that V has a connected subtree. So V appears here, here, and here. So the last condition is that for every 3 bags, B1, B2, and B3, if B3 is on the path from B1 to B2, so I just write it like this, then I should have V of B1 intersection with V of B2 is a subset of V of B3. Okay, so if B3 is, for example, this vertex, it's on the path from B1 to B2. And every vertex that appears in both B1 and B2 should also appear in B3. That's all I'm saying here. I mean, it looks awkward when you write it like that, like when you make it that formal. But all I'm saying here is that a tree decomposition is a tree of bags, such that every vertex appears in some bag, every edge appears in some bag, and every vertex appears in a connected subtree. Those are the conditions. Okay. Now, why is this even useful? Like, yeah, I said that we can use this to solve independent sets. Because basically I could take my top bag and say that this is some sort of a cut, right? But it's not that useful if you think about it, because if I had a cut of size k, so let's say this bag had k vertices in it, then I had to try all the 2 to the power of k different cases, right? So not every decomposition is really useful. For example, I can always have a trivial decomposition. I can always have a decomposition where I just have one bag and every vertex is in that one bag, right? And then if I want to use it, for example, to solve maximum independence set, I'm spending 2 to the power of n time, which is terrible. So in order for this decomposition to actually be useful, we also need these bags to be small. I need them to have a very small number of vertices in them. Right? Okay. So let's just define that concept. So I want to define the concept of width. And the width of a tree decomposition is basically the size of the largest bag. Okay? So if I have this tree decomposition T, the width of T is just the maximum over all bags of the size of that bag, which by that I mean the number of vertices in that bag. And then for some historical reasons, we also have a -1. Okay, don't ask me why. We just have it. Like the first guy who invented this put a -1, and the -1 is there. There is no good reason for it. So the width of a tree decomposition is just the maximum number of vertices in one of the bags -1. So this is, for example, a decomposition of width 2. Okay? And now finally, I can define the parameter that I really care about, which is the treewidth. And the treewidth of a graph is just the smallest width among all of its possible tree decompositions. So consider all the ways that you can take this graph and create a tree decomposition. And among all of them, take the tree decomposition that has the smallest width. And that width is the treewidth of your graph. Okay? So what is the intuition behind treewidth? Basically, it's the problem that I had here that I erased. So if you have a graph of treewidth k, and if k is small, your graph kind of looks like a tree. You can always find cuts of size almost k, and you can just break this tree down. So another way of looking at this is to say that the tree decomposition is a way of covering my original graph, right? So if I just look at my bags in my original graph, for example, I have one bag which is 1, 2, 3. I have one bag which is 1, 5. I have one bag which is 2, 6. And finally, I have a bag 3, 4. You see, these bags are covering my original graph. And if you look at how these bags are connected to each other, they are connected like a tree. Right? So this is the other way of looking at a tree decomposition and what it means. It basically means you're covering your graph with a bunch of small sets. So if my treewidth is small, all of my bags are small. So you're covering your graph with a bunch of small sets such that those sets, if you create a graph out of them, so if you put one vertex for each one of these sets, and if you connect two sets, if they intersect, then that gives you a tree. Okay? Nice. So, but we usually just use the most formal definition of tree decomposition, which is that it's a tree of bags. Every vertex appears in some bag, every edge appears in some bag, every vertex appears in a connected subtree. Okay. So based on this, let's try to prove some lemmas. Okay. This is the first lemma that I want to prove. I want to say consider 3 different bags, and let's say that one of these bags is on the unique path between the other 2 bags. So this is a tree. Between every pair of bags, you have a unique path. So I'm just saying consider B1, B2, B3 in your bags. And let's say that B3 is on the path from B1 to B2. Okay? And additionally, I want you to take 2 vertices, one in B1 and one in B2. So this is my picture. I have B1 here. I have B2 here. I have a path. And in that path, I see B3 at some point when I go from B1 to B2. And I want to say, consider 2 vertices. Let's say U1 is in B1 and U2 is in B2. Okay? So these are all assumptions. I'm taking these things. I'm taking U1 in B1. I'm taking U2 in B2. Now, I want to say that if in my original graph, I have a path that goes from U1 to U2, that path has to definitely go through this bag as well. Okay? So if P is a path in G, in my original graph, from U1 to U2, then P intersection with vertices of B3 is non-empty. That's the line. Okay. For example, let's take this bag and let's take vertex 5 in it. And let's take this bag and let's take vertex 4 in it. Now, this bag is on the path from this one to this one. So what this says is that any path that goes from vertex 5 to vertex 4 in the original graph has to go through one of the vertices in this bag. 1, 2, 3. And of course, you can check that, right? If you want to go from 5 to 4, I mean, there is no way you can avoid 1, right? And there's also no way you can avoid 3. Of course, there is a path that goes through all of them in this case. But yeah, I don't care that much about that. I really care about this. Okay, what is another way of saying this? Another way of saying this is that every one of my bags is a cut. If I take a bag and if I remove all the vertices in that bag from my original graph, then my original graph breaks down into several connected components. And actually, those connected components correspond to the connected components of my 3D composition if I remove that bag. Right? Okay, so for example, if I remove this bag and all of the vertices in it, what do I get? I get 3 smaller 3D compositions. One of them only has 5, because remember, I removed that vertex. One of them only has 6. One of them only has 4. Now, what happens if I do the same thing in the original graph? If I remove 1, 2, 3 from the original graph, I get again the exact same thing. I have one connected component that only has 4, whose 3D composition was here. One connected component that only has 5, and one connected component that only has 6. Okay? Now, but we have to prove this. How do we prove this? I can basically say that I look at this path P in my original graph, and I try to trace it in my 3D composition, right? So this path starts at vertex U1, right? Let's say that the path is something like U1, and then it goes to W1, W2, so on to WT, and then it goes to U2. Okay? So it went from U1 to W1. So that means there was an edge in my original graph from U1 to W1. So there should be some bag that contains both U1 and W1. Okay? So I start from U1 in the bag B1, and I just go to that bag, go to the bag that contains both U1 and W1, and I trace that in here. So let's say that bag is somewhere here. So this one has U1 and it also has W1. So I start from here, from this U1, and I go to this U1. And then I trace this edge in my 3D composition. There is an edge from U1 to W1, so here I can go from U1 to W1. Then I continue the same process. So when I want to go to W2, there has to be some bag that contains both W1 and W2. And it has to be connected to this bag because W1 appears in a connected subtree. So I just go from W1 in this bag to W1 in the bag that also contains W2. And then from there, I go to W2 in the same bag. And I continue this. So what does this give me? This gives me well, not exactly a path, but a walk on my tree, right? So it's a walk because I might see the same bag more than once. But it's a walk on my tree that goes from B1 to B2. But the only way to go from B1 to B2 in my tree is to also go through B3. So at some point, my walk had to go into B3. And that point, that's one of these WIs. It's a member of B3. So my path has some intersection with B3. Okay, that's the proof. Okay. But I can actually prove something even better. So until this point, I said that you can take a bag and remove it, right? And what was in my mind when I was doing this? I was saying that when I had a tree, I would just take one vertex of the tree and I remove that vertex and my tree would be disconnected into several connected components. But if I have a tree, I can also just take an edge and remove that one edge and disconnect my tree. So what does that look like? How can I explain that on a tree decomposition? So let's say I take some edge of my tree decomposition. For example, I take this edge and I remove it, right? Again, my tree decomposition would break down into several connected components. Actually, let me make my example a little bit larger. So maybe let me add 7 and 8 here. And then maybe here I can have 6, 7, 8. Okay. Now in this one, you can check that this is a valid tree decomposition. I hope that it is, if I haven't made any mistakes. So in this tree decomposition, if I remove this edge, this breaks down into 2 different tree decompositions. And it's always 2. When you remove an edge, you always get 2 connected components. Okay? So what does this correspond to in my original graph? Well, I can just take all the vertices that appear in both bags at both endpoints of that edge, and I can just remove those. So what is the intersection of this bag and this bag? It's just the vertex 2. So removing this edge corresponds to just removing the vertex 2 from my graph. Okay? And if I do that, and of course I have to also remove it from the tree decomposition. So let's say I removed it from here and here. Now what happens? So here I have a graph with vertices 5, 1, 3, 4. And I have a tree decomposition of this graph, 5, 1, 3, 4. On the other side, the other connected component is a graph on vertices 6, 7, 8. And this part is a tree decomposition for the vertices 6, 7, 8. And you can actually prove this in a way similar to the lemma that I proved before. That whenever you take an edge and you just cut that edge in your tree decomposition, that's equivalent to removing the vertices in the intersection of the 2 bags from your original graph. And your original graph will break down into 2 connected components, and each one of those connected components corresponds to one of the connected components of your tree decomposition here. So this is a valid tree decomposition for this part, and this is a valid tree decomposition for this part. Okay. Nice. So finally, let's actually solve something. So let me restore my graph and tree decomposition. So this is 2, this was 1, 2, 3. And here I had the vertex 2. Okay, and if I want to show my bags, now I have this bag as well. How would I find a maximum independent set in this tree, or the size of the maximum independent set in this tree, using this tree decomposition? Sorry, in this graph, using this tree decomposition. This is not a tree. Yeah. So I want to do something very similar to before. I want to define some sort of dynamic programming. So I say for every bag, for every bag B in B, let's define some dynamic programming variable, which is dp of B. And okay, as I told you before, we have to keep track of which vertices in this bag actually appear in our independent set. So now I can't just have one Boolean value 0 or 1. I actually need 3 Boolean bits, right? So I can say for every B in B and every, let's call it M, that is a subset of the vertices of B. I call it M because it's usually called a mask. Okay? It's like a bit mask. So dp of Bm is going to be what? So I want to find the size of the largest independent set whose intersection with the bag B is exactly the set of vertices that I have in my mask M. Okay? So this is the extension of the idea that we just had a 0 or 1 on a normal tree. So we now have 2 to the power of k different cases. But another point there was that I was always solving the problem in the subtree. So I have to somehow define a subtree here, and I have to also define the subgraph corresponding to a subtree. Okay? So let's do that first. So first of all, I say that for every bag B, whenever I write T sub B, this just means the part of my tree that is rooted at B. So B and all of its descendants, the subtree of B. Okay? But I have to also say what that subtree corresponds to in the original graph. So for that, I define something called G sub B, which is the part of my original graph that corresponds to this subtree. Now, how do I define that? So I have to say which vertices and which edges, right? So this is going to be, okay, I can't write V of B because I've already used that. Okay, so let me just put an arrow here and here. Okay, so I say that this is the vertices below B and the edges below B. Now, what does that mean? What is the vertices below B? That's just all the vertices that appear in any bag anywhere below B. So union over all bags that are in the subtree of B of the vertices in those bags. Okay? So for example, if my B is here, I just take this vertex and all of its descendants, which in this case is just these 2 bags, and I just look at all the vertices that appear there. So 2, 6, 7, 8. Okay? Now, how about the edges? What are the edges in this subtree? Well, I just take every edge that appears in some bag here, right? So for example, I have 2 and 6 here together, and there is an edge between 2 and 6. So I say that edge is in the subgraph corresponding to this bag. And here I have 6 and 7. There is an edge between 6 and 7, right? And I just do this. Okay, so the edges in the subgraph are basically the union over all bags that are in the subtree of all the edges E equal to UV, which are in my set E, such that both U and V are in that bag. Okay. Again, don't get confused by the set notation. It's just that I'm taking this bag, I'm finding all the edges that have all of their endpoints in this bag. And then I'm doing the same thing for all of its children and all of its children's children and so on. That's what I'm getting here. So whenever I write the subtree of B, it just means the part of the tree that is from B and down. And whenever I say the subgraph of B, It's just the part of the graph whose tree decomposition is this part of the tree. Okay. So now finally I can define my dynamic programming. I can say that I want to find the size of the maximum independent set. And for every bag B and every mask on the vertices of B, so for every subset of the vertices of B, I define dp of Bm to be the size of the largest independent set, but not in the whole graph, in the graph that corresponds to this bag in G sub B. Now, I have to also use my mask. I want that independent set, so let's give it a name, the largest independent set I, such that the intersection of that independent set with my bag is my mask. Okay? In other words, the way I'm breaking my problem into smaller problems here is that I'm saying consider some bag, for example, this bag, and then just consider the part of the tree that is below this bag and the part of graph that corresponds to that part of the tree. Okay? And also in this bag, let's choose which one of our vertices appear in the independent set and which one doesn't. And I'm just doing brute force here. I'm considering all the 2 to the power of k cases. And after I decide this, tell me what is the largest independent set in that graph that has exactly that intersection. Okay. Now, how can I compute this? So first of all, it's super easy to compute them at leaves, right? So if I have, if B is a leaf, so let's say it's L, a leaf L, and I have some mask. Now, if this is a leaf, the graph corresponding to it is very easy to compute. It's just a set of vertices and edges that appear in this leaf, right? And I also have a mask that tells me which one of them I have to take and which one I cannot take. So I just check if the set of vertices in my mask is really an independent set. If it is an independent set, then the answer is the size of the independent set. If it's not an independent set, then the answer is that this is impossible. And the way we show impossibility here is that we just say it's minus infinity. Okay? So if no such I exists, I just say that the value of my dynamic programming is minus infinity. Okay. So computing it at the leaves is easy. What if I want to compute it at a bag that is not a leaf? How would you do that? So let's say I want to compute it here. Let's say this bag is B1, this bag is B2, this is B3, B4, and B5. Okay? And let's say I want to compute dp of B1 and, for example, just 2. Yeah. So what does this mean? This means that I want to take the largest independent set from the graph corresponding to the whole tree, which is the whole graph. And I want my vertex 2 to be in the independent set, but I definitely don't want 1 and 3 to be in the independent set. And all the other vertices, I have a choice. Okay, so for all the vertices in the bag, I know whether they're in the independent set or not. For all the other vertices, I can choose. Now, how would I compute this recursively? How can I write a formula for this? Okay, so here's the thing. I know what happens to vertices 1, 2, and 3, right? So I know that 2 is going to be in my independent set, and 1 and 3 are not going to be in my independent set, right? So what can I do? I can immediately just remove this bag and remove its corresponding vertices from the original graph, right? But as I'm doing that, I have to be careful. I have to be careful that if I remove, for example, 2, since 2 was supposed to be in my independent set, I have to mark all of its neighbors as not being in my independent set. So I first move 6 as not being in my independent set, and then I remove all of these. Now this is what I have to solve. I have to say what is the largest independent set of this remaining graph such that it does not contain the vertex 6. Because I have included 2 and 2 was a neighbor of 6, so I can't include 6. So in other words, if I want dp of b1 and 2, I have to just look at all of its neighbors separately, right? First of all, I have this vertex 2 in my independent set, so that's 1, plus whatever number of vertices I can get from this child, right? So dp of b2, but what are my constraints on vertices 1 and 5? Well, vertex 1 is not going to be in my independent set, right? Because, let me put this back. So here we had 1, 2, 3. And since I'm computing dp of b1 and 2, I know that 2 has to be in my independent set, but neither 1 nor 3 are in the independent sets. Okay? So when I'm doing dp of b2, I know that 1 is not going to be in my independent set, but I have a choice about 5. So it's going to be the maximum of dp of b2 and empty set, which is the case where I don't take 5, or dp of b2 and 5. But I know for sure that I cannot take 1 from b2. Now I can continue the same thing. Actually, let me continue it on this board. So plus, what happens in this child? I have b3, and I know that 2 had to be in my independent set. Okay? So this is just going to be maximum of dp of b3, and 2 has to be in the independent set, but I have a choice about whether I put 6 or not. So b3 2 or dp of b3 and 2 6. Okay. Now, of course, dp of b3 2 6 is minus infinity. We will know that later because there is an edge between 2 and 6. Okay, but this is what we get from that side. Plus, okay, what about this part? So I have 3 and I have 4, right? And I know from this part that 3 shouldn't be in my independent set. So I have a choice whether I put 4 in my independent set or not. So plus the maximum of dp of b4 and just 4, and dp of b4 and empty set. Okay, and by the way, I don't need the 1 plus, I just realized, because that 1 was this vertex 2, and it's counted in b3 anyway. So I count it here anyway. I don't need to add it again. Okay, so how can I generalize this to the general case? So I have some dp of bm, right? And I have this bag B, and let's say it has a bunch of children. Let's call them C1, C2 to CR, because they're children. Okay? So what do I know about what happens in each of these children? So in C1, for C1, I have to choose a mask but that mask has to not have any conflicts with the mask that I have at B, right? So this is the thing that I choose at C1 is just going to be dp of C1 and M1, but what condition should M1 have? M1 intersection with B should be M, right? Or actually a subset of M. Let's be more specific about this. So what are the cases? One case is I have a vertex here that also appears here. In that case, this vertex should be in M1 if and only if it's in M, right? So let's just do that. Let's say that I say M is, I write it like this, which means M and M1 fit together if and only if for every vertex V that is in both this bag here and also this bag here, I have that V is in M1 if and only if V is in M. Okay, so that's the definition of two different masks actually fitting together. So they don't have any contradictory information about any vertex, right? So I have to just take a mask M1, but which one should I take? Well, I want to take as many vertices as possible from this subtree. So I just take the maximum of the dp of C1 M1 over every M1 that has no conflict with M, right? And then I do the same thing for every one of the children. So here I can just say Mi, and here I can say Ci and Mi, and then I have to sum over all the children. Okay? And finally, there's just one more point. We might have a vertex that only appears here and also appears in our mask, but doesn't appear in any of the children. We have to add those vertices to our total, right? So plus this whole thing, plus the number of vertices that only appear in B and none of the children, and also appear in the mask. So I'm not going to write it, but that's what you have to do. Okay, now as you see, this was very complicated, and we will see how to simplify this very soon. But what is the runtime here, finally? So let's say that the width of my decomposition was K. So every bag has at most K vertices, or K plus 1 vertices. Okay? How many different dp variables did I define? Well, for every bag, I defined 2 to the power of K, to the power of K plus 1, but I don't care about constants, so just 2 to the power of K variables. So my number of variables is just going to be O of 2 to the power of K times the size of B, the number of bags. Okay? And then how much time do I spend to compute each one of these? Well, you see, for every variable, here I'm going over all of the children, but I can go over each child separately. And for every child, I'm just trying to see what are the masks that don't conflict with my current mask. So I have 2 to the power of K different masks that I can try here. So basically, I'm spending this, okay, actually, times another 2 to the power of K. So I have these many of these variables, and at each one of them, I'm doing 2 to the power of K computation, right? And another way of seeing this is that you can see that for every edge in my tree decomposition, so this part here corresponds to taking any child of any vertex, any child of any bag, which corresponds to taking any edge. So for every edge, I'm doing 2 to the power of k computation. So my total computation is going to be number of edges, which is just, it's a tree. The number of edges and vertices is the same, times 2 to the power of k. And of course, the other 2 to the power of k is from the masks. So my overall runtime is now 4 to the k times the number of banks. Okay. Now, this is a terrible algorithm. We will see how to really reduce this, and we will actually reduce this to 2 to the power of k times number of banks. But before I talk about making this any better, I want you to just, again, see the intuition here. The intuition here is that when I want to solve this, if only I know exactly which vertices of the current bag are going to be in my independent set, then whatever decision I make in each of these parts is going to be completely independent of the decisions that I make in the other parts. And this is because of that cut lemma that we had. Okay? So, now, another really important question here is, what is the number of bags? Right? So let's say I give you some graph. That's what I give you in the inputs, the main graph. Right? I don't really give you any kind of tree decomposition. So you probably have to compute the tree decomposition yourself. And if you compute that, what is the number of bags that you're going to have? Now, actually, computing tree decompositions is a much more advanced topic, and we're not going to cover that. But just know that there is an algorithm that finds if your Treewidth is bounded, finds an optimal tree decomposition in linear time. Actually, its runtime is something like O(n) times some function of k, where k is the Treewidth. Okay, so it's linear time FVT with respect to Treewidth. Actually, another point I should mention is that if I just give you a graph and I ask you what is the Treewidth of this graph, that's an NP-hard problem. Okay, so it's NP-hard, but if the answer is small, it's FVT. So if I give you a graph and you know that I have somehow guaranteed that this graph is going to have bounded Treewidth, for example, because it was created by a process that creates tree-like graphs, then you can just run like a standard algorithm, and there are a lot of tools for this, and it will give you a tree decomposition with basically n bags. So from now on, I'm just going to assume that the number of bags is also n. Okay, so I'm just going to assume that the number of bags is the same as the number of vertices in my graph. So instead of 4 to the power of k times number of bags, I just say that my runtime is 4 to the k times n. Okay. Now let's talk a little bit about how we can make things better. So our algorithm here was quite weird, and we had to do a lot of weird stuff there, basically. We had to spend 2 to the k time just to compute one dynamic programming variable. But why was that? Well, if you look at this expression here, we have two problems. One problem is that I might have a bag that has a lot of children, right? And then I have to go to each of its children separately. And that's why I have this sum here. The second problem is that the set of vertices in this bag can be very different from the set of vertices in its children. So when I have a mask on this bag, I have no choice but to just try every possible mask at every child, right? And that's actually where I'm getting this extra 2 to the power of k in my runtime. So I just want to define some notion of tree decomposition that solves these two problems. And this is what I call a nice tree decomposition. So what is a nice tree decomposition? A nice tree decomposition is a tree decomposition that has these nice properties that I said here. And people really call it nice tree decomposition. This is the official name. Okay, so a nice tree decomposition is defined like this. So a tree decomposition is nice if it has the following cases. So first of all, I want my leaves to be trivial. So I say that in a nice tree decomposition, I want all of my leaf bags to be empty. So for every bag B, if B is a leaf, then I want V of B to be empty. Okay? And let's say I want it for the root as well, just for good measure. So V of root is also empty. Okay, and as you see, I can easily have this condition here because I can just add an empty bag here, add an empty bag here, and so on. So make sure all of my leaves are empty. And for the root, I can just add an empty bag above it and say that now my root is also empty. So if what I want to show you is that if I'm given any tree decomposition, I can make it nice. Okay, so these are the first two conditions, but I want another condition as well. I want to say that the degree of every bag should be at most 2, or the number of children of every bag should be at most 2. So no bag has more than 2 children. Now, why is this achievable? So for example, if you look here, I have a bag and it has 3 children. How can I change my tree decomposition so that every bag has at most 2 children? Well, I can just take a copy of this bag. So I have this bag 1, 2, 3, and I just take another copy of it, another 1, 2, 3, and then I separate the children. I give one of the children to the original bag, and the other 2 I give them as children to the copy. Right? So if my original tree was a valid tree decomposition, this is also a valid tree decomposition. You can just check it. And even if I have more than 3 children, I can just take more copies of that bag, and then I can make it so that my tree decomposition becomes binary. Finally, I said that I don't like it when I have a bag here, and the set of vertices that appear in this bag are very different from the set of vertices that appear in its children. So I just don't allow that in my tree decomposition either. So I say that if I have some bag B1 and it has some bag B, let's say, and it has a child C in my tree decomposition, then I want the set of vertices in B and the set of vertices in C to differ by at most 1. Okay, and delta basically means like the delta between 2 sets is the set of elements that are only in one of the 2 sets. Okay, so that's literally the difference between the 2 sets. So for example, here I have 1, 2, 3, and here I have a child that is 1, 5. What is the delta? The delta is 2, 3, and 5, right? But I want to make sure that the delta between any 2 neighbors or any child and its parent is at most 1. So how can I achieve this? Well, I can just add a lot of internal vertices, in a lot of internal bags. So I had 1, 2, 3. Let me just do it like this. And then I had 1, 5. Right? And they were directly connected. Now I want to just add some bags in the middle so that every bag differs from its parent in only 1 vertex. Okay? So I start here from 1, 2, 3, and actually I know that I have to only keep 1. So I have to get rid of 2 and 3, but I get rid of them 1 by 1. So first I get rid of 3, then I get rid of 2. Right? And then I have to add the elements that are here, but not here. But that's just 5, so I don't need any more internal bags here. So you see, again, you can see that this operation keeps your tree decomposition valid. So what did I just prove? I proved that if I give you a tree decomposition, you can always make the tree decomposition nice. Okay? And how much time does it take? It's actually quite easy to see that this can be done in linear time, all of the operations that we talked about. So it's going to take O(n) times maybe k squared. Right? I don't really care about the dependence on the Treewidth because Treewidth is small, I'm assuming. Treewidth is my parameter. So in linear time, I can take my tree decomposition and I can make it nice. So what does this mean? I told you that if I give you a graph, you can find an optimal tree decomposition in linear time. That's an algorithm we're not going to cover. But then I said, if I give you a tree decomposition, you can make it nice in linear time. And this process of making it nice does not increase the width of the tree decomposition. You can also just verify that, just go over all of the steps. There is no case where you create a bag that is larger than a bag that you previously had. Okay? So basically, if I give you a graph and that graph has bounded tree widths, in linear time FVT with respect to the tree widths, you can find a nice tree decomposition that is also optimal. Okay, but now let's say I want to run this algorithm, the algorithm that I had for maximum independence set, but instead of running it on just any tree decomposition, I run it on a nice tree decomposition. Okay, now what happens? Well, first of all, what happens to this sum? You see, previously, I had to go over maybe R different children. I didn't know what the number of children was. But if I have a nice tree decomposition, I know that the number of children is at most 2. So this sum is at most going to go up to 2. So that's much faster and nicer. What do I know about this one? So let's say I have a mask on this bag. And I want to find all the masks that do not conflict my original mask on this bag. But what do I know here? I know that the difference between these two bags is at most 1 vertex. So either there is a vertex in B that is not in C1, for example, something like this. There is a vertex V in B, but it's not in C1. In which case, in C1, I can only have 1 bag. Right? Because every vertex of C1 is also appearing in B. And then the mask for B tells me exactly what the mask for C1 is going to be. Right? What is the other case? The other case is that there is a vertex, for example, let's say there is a vertex U in C2 that was not in B. But again, the difference between C2 and B can be at most 1. So this is the only vertex that is in the difference. Right? So if I have a mask for B, it tells me what I have to do with all the bags, with all the vertices in the bag C2, except for that 1 vertex. And that 1 vertex has 2 cases. It's either in or out. So in other words, here, I have to again only look into 2 cases instead of 2 to the power of k. Right? So what is my total runtime now? Well, I had n times 2 to the power of k plus 1 dp variables, right? But now to compute each one of them, I'm spending constant time, basically, right? Now, it's not exactly constant time because I have to do some local checks as well, right? So for example, it might be that I have 2 vertices here that are in my mask M, and they already have an edge between them in the original graph. So in that case, I said that I set this dp value to -infinity. So now actually that check is going to be our most expensive operation. And that check is going to take k squared time because I'm taking every pair of vertices and just checking if there is an edge between them. So this is times 2. times k squared. But again, I don't care about constants, so let's remove these constants. And so my total runtime is n times 2 to the power of k times k squared, which is much better than 4 to the power of k times n. Right? And I got all of this by just converting my tree decomposition to a nice tree decomposition. So normally, whenever you're working with tree decompositions, usually all of the algorithms start by making the tree decomposition nice. Okay. Now, final word. The same idea can be applied on virtually any other problem that you can solve on trees using dynamic programming. So if I give you a tree and I ask you for the size of the largest clique, or if I give you a tree and I ask you for the smallest vertex cover, right? All of these problems, you can do a similar dynamic programming on the tree and find a solution for them. And then you can extend that dynamic programming in a largely similar way to a dynamic programming over the tree decompositions. And so as long as your Treewidth is bounded, you can pretty much solve anything you can solve on trees. There are some cases where we know how to solve something on a tree, but not on tree decompositions, but they're rare. Okay. Now, let me see. Yeah, I just want to define some other parameter here as well, and we will use it later. And that parameter is called the pathwidth. Now, this one has the sound that I cannot make twice. Okay? So when we wanted to define treewidths, we wanted to have a tree decomposition. So we wanted to embed our original graph into a tree. Now, just imagine that instead of using a tree, we use a path. And we keep everything else the same. So instead of having a tree decomposition, we have a path decomposition. Our decomposition is just a path. So it doesn't branch at all. Then that's the way we can define pathwidth. So if I take all the decompositions that are just a path, I can define the widths for each one of them, which is the size of the largest bag minus 1. And then I can say that the pathwidth of a graph is the smallest width among all of its path decompositions. Okay? Now, why is a path decomposition interesting? Because basically, a path decomposition is a decomposition that doesn't branch. So it looks like this. It's just a path. Right? So especially if I make it nice, I have a situation where every bag has at most one child. Right? So I have like one leaf bag that doesn't have any children, but all the other bags have exactly one child. And for some algorithms, that's really useful. For some algorithms, you don't want to have to look into two different children. And yeah, so that's the definition of pathwidth. So in the next session, we will see some more techniques about how you can solve problems using tree decompositions. What we saw today is called, unsurprisingly, dynamic programming on tree decompositions. Next session, we will also see kernelization using tree decompositions.